Hello everyone, welcome back. Considering we just finished talking about pressure at depth, I wanted to bring up a few common problems that you're most likely going to see along the way, just to make sure when they do come up, you know exactly what you are looking at and you know what to do. So to start out, we are going to begin with this problem. Now this situation you've probably done yourself. It's what happens when you take a straw, put the straw into a drink, put your finger over the top, then lift the straw out of the drink. You will find that the juice, milk, or water, or whatever, actually comes with the straw. It's held in place inside the straw as long as your finger remains over the top. If you were to release your finger, then all this fluid would drop out. So let's take a look at why this happens. And along the way, we're going to answer a really common question. And that question is going to be this. Outside the straw is regular atmospheric pressure. So I'm going to put a little P0 right here, which is this value, 1 times 10 to the 5 pascals. Now, the question for this problem is going to be, what is the pressure inside here, which I am simply going to call Px. Now, this can't be atmospheric pressure because if these two pressures were the same, then the force from the Earth would simply pull the water down out of the straw. So we are going to do a complete analysis of this problem, and we're going to do it two ways to really bring the point across. Now, along the way, they're going to cross paths very quickly, but this will be a good way to show that you can solve this problem using two different points of view. So first, let's make a few things clear. I'm going to use some numbers that are definitely not to scale, just to make the math easier. So I'm going to say the area on the bottom of the straw is 0.4 meters squared. And I'm going to say the water column here, we're going to say again that the liquid's water, and the height is 2 meters. Again, absolutely not to scale, unless this is the Jolly Green Giant. But again, I want to keep the math simple for my explanation here. All right, like I said, we're going to talk about this two ways. First, we're going to discuss this in terms of forces. Now, to do that, we are going to use our tried and true method of creating a force diagram. First, force Earth on water. Gravitational force of the Earth pulling down on the water. Also downward is going to be force X, which is force from the air pressure inside the tube here pushing down on the water surface. Now to balance that, upward is going to be force, I'm going to call this force naught because it's force from the air pressure, which again is 1 atmosphere or 1 times 10 to the 5 pascals. So under forces here, let's set our equality. Force naught equals force Earth on water times force X. All right, I am now going to expand that. First, using our basic pressure equation here. Pressure naught times area equals mass of the water times G, mg, which is force Earth, plus pressure X times area. Now I'm going to expand this again because we can break up this one in the middle even more. And to do that, I'm going to use this one right here, the density formula. So I get mass in terms of density. So we have density of water times the volume of water times G, plus pressure X times area. Now I'm going to keep going because this could be broken down again. And a little note, the technique I'm using right now is a very important overall technique for physics. Just breaking things down until you get to the very basics of the variables you have. So what I'm breaking down here is going to be the volume. Now the water is in shape of a cylinder because it's in a straw, and the volume of a cylinder is the area of one side times the height of the cylinder. So I have area times height times G plus pressure X times area. Now what do we have here? It looks like area can be canceled. It's in all parts of the equation here, which means I can just cancel it out, which means the area over here was actually completely irrelevant. I'm just going to rewrite what I have now, so I get pressure naught times the density of the water times height times G times pressure X. I'm just going to isolate pressure X now, which is pressure naught minus density height G. Make a little room here. So pressure X equals 1 times 10 to the 5th pascals plus density of water times the height times G. Now, kilograms cancels. One of these meters cancels, so we get meters squared, which gives me newtons per meter squared, which is pascals. which gives me 80,400 pascals, which is definitely less than atmospheric pressure. So that will be the pressure between your finger and the top of the water line. If you were to take your finger off of here, then the air pressure would stabilize with atmospheric. This force X would increase and you would have an unbalanced force downward and the water would begin to accelerate downward. All right, now let's take a quick look at this from the point of view of pressure, because I want to relate this to the last video in the series, which is pressure at depth. And to do that, we're going to take a look right here, right where the bottom layer of water particles are touching the atmospheric pressure of the air. So again, you have atmospheric pressure pushing upward, and you have the pressure from the water particles pushing downward, because again, pressure pushes in all directions. So if we take a look at that spot right there, I'm going to make a similar diagram to a force diagram, except it looks like this. Pressure upward from the atmosphere and pressure downward. But this is absolute pressure. So I'm actually going to use the ABS symbol here. Except this time, you're not adding actual atmospheric pressure. You're adding this because this is the pressure above the waterline. Pressure X. Watch what happens when I write that equation out. Pressure naught upward equals pressure absolute, which is pressure X plus pressure at depth, which is rho G H. Now, I'm not even going to bother continuing from here because if you notice, what I just wrote is exactly what we have here. It's the same thing. So in other words, thinking about it in terms of forces and thinking about it in terms of pressure, you come to the exact same conclusion along the way, and the rest of it is just math. So for forces, we did the force diagram of that column of water. We treated it like an object, which it basically is. It just made out of fluid. From the pressure point of view, we took a look at one spot and said, well, that water line, those particles are not moving. And if that area right there is not moving at all, then the pressures have to be equal. Pressure up is atmospheric and pressure down is absolute pressure, which includes pressure X plus the pressure at depth from the water. Once you get to that point, it's just a game of solving what you were looking for. Here, we were looking for pressure X, which is pretty common. They could also give you pressure X and say, how high is the water column? So it doesn't matter. Once you get to this point, it's just a game of, okay, what do I have and what am I missing? And this also explains why that water column doesn't go anywhere. All right, so the next problem I want to look at is actually very closely related to the one we just did. And it is about you drinking from a cup or something with a straw. So when you do that, you put your lips right here and we say suck up the water. However, let's take a look at what is actually happening. In our minds, some people will think, oh, you are somehow pulling the water upward. You are not. What you are doing is this. You are lowering the pressure right here. This basically is pressure X from the last problem. You are making that lower than atmospheric pressure. Because don't forget, pressure can't pull. Pressure can only push. So the pressure in here is pushing downward on the water column here. However, what is happening at the same time is atmospheric pressure is pushing on the water surface here. So what is actually happening is you are not pulling the water up. Atmospheric pressure is pushing the water down and forcing it to go up the straw. And it can do that because this area right in here, the pressure is lower than atmospheric. Because remember, the pressure has to be equal at each horizontal point. So the question then becomes, what is the lowest pressure you can have here? If you are drinking out of a straw or something, and the water is going up the straw because you are lowering the pressure above the water column in the straw, what is the lowest the pressure can go? Well, the pressure cannot go negative because pressure can't pull. This means the lowest the pressure can be is 0 pascals. Once you get to 0 pascals, this water column is not going any higher. Because if you think about it, if you put a lid right here on the cup surface, an airtight lid, and put the straw through it so it's still airtight, you would not be able to draw this water too much up the straw because the pressure in here would reduce, And that means there would not be enough pressure to push this water down to go up the straw. If you ever want to try this out, stretch a rubber top or a balloon over a cup and stick a straw through it, then start to drink. You will see the balloon bend downward because the atmospheric pressure is pushing the balloon downward as you start removing pressure from inside the straw. Eventually, you'll get to the point where water simply cannot go up the straw anymore. That literally means there is a limit to how long this straw can be. Let's find out what that limit is. All right, so let's see how high this water column can go. First of all, at the surface here is pressure naught, which we have right down there. The equation we derived from our last problem, we're still just going to use this point right here. So to be clear, we're at a point where the pressure here is 0, the water column is raised, and nothing is moving, so this is still a static problem. At this point right here, we still have pressure naught pushing upward on this water column, and absolute pressure pushing down, which is px plus rho gh. We just derived it in our last problem. Now, we flat out just said the lowest pressure can be px is 0, so I'm just going to cut this out. So taking this equation rearranged, the height of the water column is going to be pressure out of atmosphere divided by the density of water divided by g. 1 times 10 to the 5th newtons per meter squared, or pascals, 1,000 kilograms meters cubed, and 9 newtons per kilogram. So let's see, newtons cancels. Kilograms cancels. I have meters squared here and meters cubed here, so this ends up with 1 over meters. I'm dividing by a fraction, so this flips. And that is going to ensure that I get the unit of meters, which is what I'm looking for. And that is 10.2 meters. Now, this actually has some historical significance here. This means that if you have a pump that lowers pressure and you're trying to draw water up from a well, this is the highest it can go. Again, pressure can't go negative. The lowest this can possibly be here is 0, so the highest the water column can possibly be, assuming atmospheric pressure doesn't change, is 10.2 meters. In imperial, that is a little over 33 feet. Now, an interesting historical fact, the typical floor of a household is 14 feet from one floor to another. That means if you're drawing water up from a well using this technique, you can only get it up a little over 2 floors. This is actually why a lot of old architecture for buildings people are actually going to live and exist in rarely go above 2 floors. If you look at any of the Old West movies in America, they're all 2-floor buildings unless they have a 3rd floor that's only for storage. You're not going to put a living space on the 3rd floor if they cannot have a sink and a bathroom. In other words, they could not get water that high. So a very obvious question becomes, okay, how then did they get water to the top of a building that is, say, 10 stories? Well, so here's my building. Let's say it has 8 to 10 floors or something. So in this situation, when you need the water to go up, say, the 10th floor, you have what are called booster pumps. What happens is you have the first pump to get it to the 2nd floor. Then you have that pump. Then you either store water in a reservoir or you have another pump increase pressure from there and get it 2 floors higher. And then you repeat the process. In other words, this water column can go 10.2 meters high from wherever the water currently is sitting. So if it's already sitting on the 2nd floor and you do it again, you can then get it to the 4th floor, then the 6th, then the 8th, etc. Now, the goal typically is to put it in a reservoir that is on the roof, because if you have a large reservoir of water on the roof, then all you have to do is let gravity run its course. If you let this water run through the pipes in the building, then the water in the pipes is going to be at a higher pressure than the water in the reservoir because it is simply lower. In other words, once you get the water up there, gravity does the work for you. So what will typically happen is these pumps work continuously to maintain a level water line in the rooftop reservoir. People get up in the morning, take showers, etc. They start using up the water in the rooftop reservoir. And when that starts to happen, the pumps kick in and start drawing water upward and putting water back in the reservoir. This way, the people in the building are not actually dependent on the pumps. They're depending on the water already stored. So this is one method on how you can get water past the 2nd floor. All right, there's one more thing I need to show you here, and it's that what I just showed you here with the water column is not typically done with water, but what it is typically done with is mercury. And this is how a mercury barometer is made. So first of all, this tube or a straw, they cap it. And in here, this is 0 pressure. Now, a water column is 10.2 meters tall. That is very high. But if you can make this device using a much more dense fluid, then the water column will not be as tall, and you could actually have it in the room of a house. You're not going to have it in a room if this device is 10 meters tall. So let's take a look at how tall this would be if we use mercury. Now, mercury has a density of 13,600 kilograms meters cubed. I'm going to use the exact same formula we had over here, which is atmospheric pressure over the density of mercury times G instead of water this time. 1 times 10 to the 5th pascals, 13,600 kilogram meters cubed, 9.8 meters per kilogram. We already did the cancellations over here, and this would come to 0.75 meters, or 2.46 feet, just to give you an idea. So a mercury barometer is something you can have in your room. This is a device that meteorologists use to actually help predict the weather. Because if atmospheric pressure is 1 times 10 to the 5th pascals, then the height of the mercury column is 0.75 meters, or 75 centimeters. If, however, atmospheric pressure changes, which it does, then the height of the column is going to change. If atmospheric pressure increases, then the height goes up. If the atmospheric pressure decreases, then the height goes down. And this is how a meteorologist can tell if the barometer is in a high pressure or low pressure zone, and then make predictions about what is going to happen in the future. In fact, every now and then, if you look around, you actually may see pressure talked about in terms of centimeters of mercury. If you ever see that, this device is exactly what they are talking about. At standard atmospheric pressure, a barometer will have a mercury column of 75 centimeters tall. If air pressure increases, it goes up, and if air pressure decreases, it goes down. And as stated, this is a device you can literally have in your room. This one you cannot, because your classroom is probably not 10 meters tall. All right, this video is running a little long, and I know I promised to keep them under 20 minutes each. Not to mention having a standalone video on the barometer is probably a good idea because it's very common and a very good situation to know. So, I am going to make a second video with some more common problems, and I'm going to end this one here. So, be sure to check out my next video for a continuation. Have a good day. This is Mr. M, signing off.